Alright, so what we're going to move into is a special kind of equilibrium. It's for solubility. Okay? And what this is last year you were given a list of solubility rules. And we said, alright, all of these compounds are always soluble, and these are insoluble. And so we said, alright guys, NaNO3, it's always going to go to Na plus and NO3 negative. Right? Because in water, if you had 1,000 of these, like 999 of them would become Na plus and NO3 negative. Okay? And so we just say, alright, we're going to err on the side of the majority, and we're going to write it like that. Okay? But what was really happening was this is an equilibrium. It could be on either side. It could be broken up or together. But the K for this is huge. Okay? That means much greater than. Okay? It's huge. And so what that means is there's so much product in relationship to the reactants that we just called it all the way over there. Well, on the flip side, we got things like calcium carbonate, which is supposed to be on our insoluble list. And so we did not, well, we had this option, like, does it split up? And so we always said it's insoluble because if you had 1,000 of these, maybe 20 of these would actually split up, so most of it would stay over here. Maybe 980 would stay over here. And so we just wanted to err on the majority and say, we're going to leave it together. And that's still how we're going to write net ionic equations. But really what this is an equilibrium, but the K for this is really, really little. And so all that means is most of it stays as reactant. But it's still, some of it does split up. And so what solubility equilibrium says is, all right, how much does split up? And we want to know this because in your water samples and all that kind of stuff, there are some insoluble compounds. There's some bad things in there, like there's some lead, and there's some iron, there's some other things that could damage you. And we want to know exactly what kind of concentrations, how much of them are going to be dissolved, and how much of them would just sit at the bottom of the solid and not flow into our water systems, like we would see it at the bottom of our cups. But we can't see calcium dissolved in water. It's Ca2 plus in water is invisible, and you would never know that you're drinking it. So the equilibrium for this is called solubility product. Okay, and I'll show you why it's got that product in there. But solubility, it means you're dealing with slightly soluble compounds. Okay, we don't mess with the ones that are completely soluble, like NaNO3, because most of them are going to be over here, and we already know that we should expect those to be there. Okay, so when a soluble ionic compound dissolves, it goes pretty much completely into ions, and so we just know that they're there. But when an insoluble one is there, it does dissociate for a small amount, so we want to figure out how much. So an equilibrium exists between the solid and the aqueous ions. It goes back and forth. So an example is, all right, lead sulfate here goes to lead 2 plus and SO4 2 negative. Well, the K for this reaction, it just has a special subscript, and it means solubility product. That means you're dealing with the solubility of something, just means it's splitting up. Okay? It's the same as before, except for in a solubility product, the solid is on the left. I mean, that's what you've got because you're dealing with is a solid soluble. And so when you write the K for this, you only would have the Pb2 plus and the SO4 2 negative. And that's what our K would be. You wouldn't have the solid that's the PbSO4. And so why it's called a solubility product is you end up multiplying the ions that are soluble, and you won't ever have a denominator because the reactant is always a solid. With this particular kind of reaction, the reactant is a solid because you're dealing with solubility. Okay? That's it. And so here's the actual value for that. And you can see that's a really little number, which means it does split up, but they only have a very little amount. Okay? And so here's the one for copper hydroxide. And you end up with a squared on the hydroxide, but that's the only difference. Okay? So there's an exception that, or there's a little weird one that you're just going to have to kind of know. And we're going to come back to this definitely later, but when you do have something that has a metal sulfide, like any metal with an S, when you split it up, you have to have water to split it up in the first place. When you split it up, it's going to make the metal and the sulfide. But sulfide by itself, when it's put in water, it will immediately hook onto the water, grab an H from the water and make HS negative, and OH negative. It just does that. So you just kind of have to know that S2 negative in water just immediately does this. And so it's kind of sneaky the way that they write this, because all of a sudden this just automatically becomes these two things. So we basically replace that with these two items in the solubility product. So here it's showing you adding these two reactions together, and we don't include the liquid or the solid, but all they did was you put the HS and the OH negative in for S2 negative. And there's our KSP. Okay, and this is important because we're going to talk about acids and bases soon, and that right there is important to bases. So this is just kind of a weirdo. When you find an S2 negative, you've got to replace it with HS and OH negative. But we're going to practice these. So we're just going to write solubility, the ion product expression for each of the following. Well, to do that, you need to just be able to write a solubility reaction. So magnesium carbonate, you need to be, alright, this is magnesium carbonate. And with our solubility rules, it's supposed to be insoluble. Okay? But it splits up a little bit, and you got to just go, alright, it splits up into Mg2 plus and CO3 2 negative. And then when you write the K, it's just a special. That's all you're indicating is its solubility product. And you go Mg2 plus and CO3 2 negative. And you just don't include the magnesium carbonate because it's the solid. All of these are going to start with solids because that's what we're dealing with. We're saying how much does the solid split up. So iron 2 hydroxide, we're going FeOH2. And when it splits up, it goes into Fe2 plus and 2OH negative. And the KSP would be Fe2 plus and OH negative squared. Okay, so you get that this little indicator, solubility product, they just named that because it never has a denominator, and it's always just a product. So when we move on to calcium phosphate, we have Ca3PO4 2, and when we split it up, it goes 3Ca2 plus and 2PO4 3 negative. And when we write the KSP, we'll get Ca2 plus cubed times PO4 3 negative squared. Okay, so this last one, this is what you need to be looking for. That's that one weird exception. Silver sulfide is Ag2S, and so when it splits up, it makes 2Ag plus and an S2 negative, and this automatically becomes HS negative and OH negative, and you just have to know that with this one. Okay, so when we write our KSP, we're going to write, alright, it's the Ag plus, and it's going to be squared, and then we have the HS negative and the OH negative. Alright, so we've got some more of these. So iron product expressions, keep going. Sodium nitrate. We would go Na plus and NO3 negative. And when you write this, you would get, alright, why do I keep forgetting the negative? Na plus and NO3 negative. This K is so large that we just consider it not even to be in equilibrium, because it's so big that these concentrations are pretty much exactly what the concentration of the original was. Okay, so you'll never see us working with this. So then calcium sulfate is CaSO4, goes to Ca2 plus SO4 2 negative, and KSP is Ca2 plus times SO4 2 negative. And since these are always solids dissolved in some water, these are always concentrations. You never are going to work with pressures when you're dealing with this. Okay, then we got chromium 3 carbonate, just to be a pain, so Cr2, CO3, 3, splits up into Cr3 plus, 2 of those, plus 3 CO3 2 negative, and the KSP is Cr3 plus squared and CO3 2 negative cubed. Then we have magnesium hydroxide, which is MgOH2, splits up into Mg2 plus and 2OH negative, and the KSP is concentration of Mg2 plus, concentration of OH negative squared. And last one, you see a sulfide. That's special. So arsenic 3 sulfide is As2S3. And then it splits up into 2, As3 plus, and 3 S2 negative. But immediately this part right here gets replaced with HS and OH negative. So our Ksp is arsenic 3 plus squared times HS negative cubed and OH negative cubed as well. It has the same, it's going to have the same coefficient in front of it. Alright, so that's writing Ksp, and now we have to talk about calculating. Okay, so the size of Ksp tells you how far it dissolves. Okay, how far right it goes. If K is big, it dissolves a lot and it's very soluble. If K is small, it doesn't dissolve as much. It doesn't dissolve very much. Okay, and something that we learned last year but didn't really talk about in a relationship is that saturation point is equilibrium. Okay, that's as much as it's going to hold, it's not going to, that's where it's going to stop. Okay, but there are two basic types, just like regular equilibrium. They can either determine Ksp by giving you the solubility, or they can ask you to find solubility from Ksp. So we did the same thing with the equilibrium. They gave us concentrations and they asked us for K, or they gave us K and they asked us for concentrations. Okay. Most solubilities in tables, and this is the same thing that I gave you last year, I gave you a big table with all the different colored lines on it, are given in grams of solute, 100 grams of water. If you're going to use these in a Ksp, they have to be converted to molarity in order to be used. Okay? And so how we're going to do that, the mass of the compound in the solution, the actual solid, is going to be pretty low. So what we're going to assume is because the density of water is 1, okay, 1 gram for every milliliter, we're going to say 100 grams is equal to 100 milliliters. And all we have to do with molarity is get the grams of solute to moles of solute, and we have to get our milliliters to liters. And then we have to divide the two. So we're going to practice with that. Okay, so here we go. Lead 2 sulfate is a key component in lead acid car batteries. Its solubility in water at 25 degrees Celsius is 4.25 times 10 to the negative third grams per 100 milliliters of solution. And it wants to know what the Ksp of PbSO4 is. So just like with equilibrium, regular equilibrium problems, you need to have an equation. So if you're doing solubility, your equation is always just splitting it up. Okay, and we have to write a K for this. Ksp is equal to Pb2 plus and SO42 negative. Okay. Now, it said its solubility in water is 4.25 times 10 to the negative third grams per 100 grams per 100 milliliters of solution. That is 4.25 times 10 to the negative third grams of PbSO4 per 100 milliliters of solution. When it says the solubility, it's saying this much will split up. This much will become these things. So when we get this into molarity, that's what these things are. That's what the solubility is. It's saying the soluble part, the part that splits, is equal to that. So we're going to take 4.25 times 10 to the negative third grams of PbSO4 and change it to moles because we need molarity. So we're going to have to go look up the masses, and we'll add lead plus sulfur plus the 4 oxygens and get 303.26. Okay, and then it already gave us 100 milliliters of solution. All we have to do to get molarity is change that to liters. And now we have molarity. So we're going to take the 4.25 times 10 to the negative third times 1,000 divided by 100 divided by the 303. Which is our answer in there. And we get 1.40 times 10 to the negative fourth. That's how much will dissolve. Will become Pb and SO4. Okay? That is what you get to put in these brackets. That's what lead is going to be, and that's what sulfate is going to be. Because for every 1 mole of lead sulfate, you're going to get 1 mole of lead 2 plus and 1 mole of SO4 2 negative. But it's only saying that much of the lead sulfate splits up, and then you just convert it to those two things. And then we get our answer by multiplying those two things together. And the Ksp is 1.96 times 10 to the negative 8. Okay, so if you look at that, we call lead 2 sulfate insoluble. It's one of the exceptions to sulfate solubility, because if you put it in water, only that much is going to dissolve, which is a really, really low concentration. So we just say insoluble for the most part, but it does dissolve a little bit. So we're going to practice again. So it says when lead 2 fluoride is shaken with pure water, the solubility, so that's how much will split up, is found to be 0.64 grams per liter. Calculate the Ksp of PbF2. Well, first we need to have a reaction, and when you're doing solubility, you're just taking the compound and splitting it up. Alright, so we're saying how much will split up of the lead 2 fluoride is 0.64 grams per liter. We need that to be in molarity. So we're going to take 0.64 grams of PbF2 per liter, and we've got to change this to moles per liter. So we need the molarity, or the molar mass of lead 2 fluoride. I didn't put the decimal place in. Alright, 245.2. Okay, so here's where you got to be paying attention. Okay, is that we need, for our Ksp, we're going to need Pb2 plus and F negative squared. Right now, we have the concentration of PbF2. That's the concentration that will split up. So we have to figure out how much Pb2 plus that will make and how much F negative that will make. And so you can do, to figure out how much Pb2 plus, you go 1 mole of PbF2 is 1 mole of Pb2 plus, and you get that answer. But if you were doing F2, or F, I'm just going to rewrite this first part. Okay, if you were going to F negative instead, you would say, alright, 1 mole of PbF2 is going to make 2 moles of F negative, and that's by the mole to mole ratio. So all this number is that they're giving you is how much PbF2 will split, and you have to turn that into what is the concentration of those ions that it does make when it does split. So this first one is 0.64 divided by 245. 0.2, and we get 0.0026 of lead, and then to make that into F, you've got to multiply by 2. So we get 0.0052. And now you have both pieces of information. This is concentration of F, concentration of Pb2 plus, that goes into your Ksp formula. Okay, so when we calculate Ksp, we go 0.0026 and 0.0052 squared. So we're going to square that and multiply it by 0.0026. And our Ksp comes out to be 7.09 times 10 to the negative 8. Alright, so we have another one. When powdered fluorite is shaken with pure water at 18 degrees Celsius, 1.5 times 10 to the negative 4th gram dissolves for every 10 milliliters of solution. Calculate the Ksp of CaF2. So we're doing solubility again. And so it tells us that 1.5 times 10 to the negative 4th grams of CaF2 per 10 milliliters of solution will split. This will split and become Ca2 plus and F2 negative. And so what we've got to do is turn that into molarity, because our Ksp is going to be Ca2 plus times F negative squared. So we're going to take calcium 4 and find the molar mass of it. So 40.08 plus 2 times 19. Get 78.08 grams of CaF2 for 1 mole of CaF2. And we want to change our milliliters into liters. So 1,000 milliliters is 1 liter. And that's going to give us the concentration of CaF2 that will split. And so our job is to turn that into Ca2 plus and F negative. And so you can skip that one calculation step, realizing that this is a 1-to-1 for calcium. So whatever this answer gives you is what calcium is going to be. And then you could do the fluoride one. That's the only one that's going to require calculation. Sometimes they both do if they're not a 1-to-1 ratio. So I'm going to do this in 2 steps. I'm going to sorry, 1.5 times 10 to the negative 4th divided by the 10 divided by the 78 times 1,000. Okay, that's going to be my Ca2 plus, and I'm going to multiply that by 2 to get my F negative. So those two answers. 1.92 times 10 to the negative 4th is my Ca2 plus. And my F negative is 3.84 times 10 to the negative 4th. Then once you have those, now you're just plugging them in. So Ksp is going to be equal to 1.92 times 10 to the negative 4th times 3.84 times 10 to the negative 4th squared. So we square our F negative and multiply it by 0.92 times 10 to the negative 4th. And we get 2.83 times 10 to the negative 11th. And that's our answer. Okay, so from solubility, you're going to have to use basically stoichiometry in order to figure out the concentrations, and then you just go plug them into your Ksp. Okay, the other way is, what if they give you Ksp and they ask you for solubility? So that's a little different. So calcium hydroxide is a major component in mortar, plaster, and cement, and solutions of calcium hydroxide are used in industry as a cheap, strong base. Calculate the solubility of CaOH2 in water if the Ksp is 6.5 times 10 to the negative 6. So we're going to write what our solubility reaction is. Okay, and then our formula for Ksp, Ca2 plus NOH negative squared. Okay, and they gave us Ksp, and we have to go solve for the solubility of CaOH2. So we're going to go kind of back to an ice diagram. But this right here, what you got to remember with solubility is that's always a solid. So we do not care about its ice part. Okay, it doesn't go into our K at all. We just don't care. But we're going to say, all right, we're dumping the solid in to begin with. So there's no ions to start with. And then some of it's going to dissolve. And how much dissolves is the same thing we've been doing. We go plus x plus 2x. And it's going to be x, and this is going to be 2x. Okay? And if you think back to what we just got done, whatever our solubility of CaOH2 was the same as the 1-to-1 ratio, the one that it was a 1-to-1 ratio with. Okay? So what we're going to do is we're going to go find x, and then we're going to say, all right, well, that's got to be the same. It's got to be a 1-to-1 ratio. That's the solubility. Okay? Because the solubility is how much did dissolve. And this right here, these are dissolved. These are ions. So all we're going to do is go over to our Ksp and plug in everything we know. 6.5 times 10 to the negative 6 equals Ca2 plus is an x, OH negative is a 2x, and it gets squared. Now you got to really pay attention to the math. We're going to simplify this side before we try solving. You have to square your 2x first, so you get x times 4x squared. Okay, and I'm showing much more steps than you probably would eventually get to, just so you know what we're doing. And now you can solve for x. If you take 6.5 times 10 to the negative 6, and you divide it by 4, and then you have to cube root it. So you got to know how to cube root on your calculator. And on this calculator, if you go to the math menu, the fourth one down is the cube root. And then all you do is type in, all right, this is your answer. And here we go. So x is 0.0118. And this is molarity. And so previously we've been giving solubilities as grams per liter. Well, you don't have to go back to that. We're just going to leave it in molarity. But that's what x is. So this is 0.0018 molar. And if I ask you to go find, all right, all that stuff did dissolve, go tell me how much of that dissolved. It's a 1-to-1 ratio. So generally the kind of shortcut is x ends up being your solubility. Okay, X ends up being the solubility, and some people call it S or whatever. That is the solubility of CaOH2. Okay, so we're going to practice some more of these. Alright, so it says suspension of magnesium hydroxide is in water sold as milk with magnesia to alleviate minor stomach disorders by neutralizing stomach acid. The hydroxide ion concentration is too low to harm the mouth and throat, but the suspension dissolves in the acidic stomach juices. What is the molar solubility of magnesium hydroxide? So what this is saying is when you take an antacid tablet, it's a base in your mouth, but they keep it they give it to you in solid form, and they use an insoluble base for the most part so that it won't dissolve on your tongue and in your throat and cause problems there. It waits down until it gets with the acid, and then it's not dissolving, it's reacting, which is different. What water does to it and what an acid does to it is completely different. Water is just trying to split it apart. An acid is ripping it apart and turning it into something else. Okay, so what we're going to do is we're going to find the molar solubility, and all that means is in molarity, which we were doing anyway. So we have MgOH2, and it's splitting apart into Mg2 plus and 2OH negative. And our Ksp equation for this is magnesium ion times hydroxide ion squared. And we're going to go back to our ice diagram because we're trying to figure out some stuff, and we don't care about the solid. Okay, but we know initially we have no ions in there. You just have the solid magnesium hydroxide. You go plus x plus 2x. This is 2x, and this is x. And this is the line we get to put in our equilibrium expression. So you get 6.3 times 10 to the negative 10th. That's our Ksp. And we've got x times 2x squared. And you're going to see this a lot with solubility. Not always, but whenever it's a 1 to 2, this is what you're going to see every time. So this is just going to become 4x cubed. That's the steps that I did before. And we're going to solve for it. So we're going to take 6.3 times 10 to the negative 10th, divide it by 4, and then we're going to go to the math menu and go to the cube root and cube root our answer, Comes out to be 5.4 times 10 to the negative 4. And this is in molarity, which is X. And X is in a 1-to-1 ratio with magnesium hydroxide. So that's our answer. That's your solubility. Okay, sometimes they're going to give you multiple KSPs and ask you, what does that mean about their solubility? And this is the important concept. The higher the KSP, the greater the solubility. Because KSP has the ions in it. This is a measure, all it is one ion times another ion. And so if that's a big number, it means the ions are a lot, and it means the solid wasn't. So the bigger the KSP, the more soluble it is. Okay, so there's a bunch of, this is just a chart of me showing how many ions are spit out, and so this is what you could figure out anyway. Magnesium carbonate is going to spit out into magnesium 2+ and carbonate, so it's just 2 ions. Okay, whereas CaF2 we did splits out into 3 ions. It spits out into 1 Ca2+ and 2 F negatives. Okay, and this just gives you the positive to the negative ion ratio, but it shows you the KSPs, okay, of each, and then their solubilities, how much will dissolve. Okay, and so if you look at their solubilities, we're just going to compare apples to apples right now and use the 1-to-1s, the ones with 2 ions. The highest KSP is sitting right here, and this is where you got to get in your head. The negative numbers, the smaller negative number is actually the larger. So 3.5 times 10 to the negative 8 is much bigger than 2.1 times 10 to the negative 10. And if you look at their solubilities that correspond, 1.9 times 10 to the negative 4th is much bigger than 1.4 times 10 to the negative 5th. Okay, so the higher the KSP, the greater the solubility. They're gonna compare. Okay, and so same thing when we look down here. These are ranked as well, with the highest solubility being, or the highest KSP being for calcium hydroxide, and it also has the highest solubility. So if they compare two things, it's just the higher the KSP, the greater the solubility. Alright, this is what we, kind of a combination of what we did with this lecture and what we did on Thursday. What a common ion is let's say I'm trying to dissolve lead 2 chromate, and I'm putting it in a solution of water. Okay, so it dissolves. If I put it in a solution of water that already has, let's say, some chromate in it, the solid is not going to dissolve as much, and you can reference Le Chalet A to explain why. It's not going to dissolve as much because the solution would already have some of the chromate, so it's going to, oops, too much of this already, and it's just going to stop. It's not going to dissolve as much, and what that'll affect how much lead will come out as well, because if not as much chromate is coming out, not as much lead is coming out. Okay, and so like if you had the solution, yay, it dissolves, and here's the KSP. But if you added some sodium chromate to it, okay, and keep in mind sodium is going to be a spectator ion, okay, because it's not part of this at all, and sodium's always soluble. But if you added some of this, you're going to make this part go up. It's going to have too much. Okay, and since KSP is constant, if you don't change the temperature, you're going to have to move that equilibrium back to the left. Lead's going to have to go down. Okay, and so what it does is it reduces how much will be dissolved. It will reduce what the X is, what can be dissolved in there. So I'm going to show you some problems with that. Alright, so it says, what is the solubility of calcium hydroxide in a 0.1 molar solution of calcium nitrate? KSP for calcium hydroxide is 6.5 times 10 to the negative 6. So we're going to have our solubility reaction for calcium hydroxide, because that's what it wants to check the solubility of. And if you notice this is a soluble compound. Nitrate is a spectator ion. It's always soluble. Okay, so that's not what they're asking. They're saying, hey, you're adding some Ca2+ in there. So what this causes, when we write our KSP, we have Ca2+ and OH negative squared. But when we fill out our ice diagram, if you're dissolving this in a 0.1 molar solution of calcium nitrate, the nitrate doesn't matter, but this is, for every 1 mole of calcium nitrate, you're getting 1 mole of calcium out of it because it's going to split up completely. It's completely soluble. So what that means is initially you're going to start with 0.1 molar of this. You're not going to have any hydroxide because you were dissolving it in a calcium nitrate solution. That's the common ion. And all this common ion means is the thing you're trying to dissolve has something in common with the thing that you're dissolving it in. So it means we already had an ion there. You still do the change the same, plus x plus 2x. This is 0.1 plus x, and this is 2x. But now when we plug these into our KSP, okay, they give us 6.5 times 10 to the negative 6 equals, and we have 0.1 plus x times 2x squared. Okay, and so now we have to do some math. We'll get 0.1 plus x times 4x squared when we square that first, because exponents come first. And then we're going to have to distribute it. So we're going to get 0.4x squared plus 4x cubed. Alright, so this is a cubic solution. When we have to do this, we're going to get 3 answers out of this. And you would get 4x cubed plus 0.4x squared minus 6.5 times 10 to the negative 6. And I'm going to show you how to do it on the calculator, but again, AP is not going to require you to do this. But we're going to go to our apps and apply simult. And enter this into a polynomial root finder. But this time the highest array we have is a 3. So I'm going to arrow over and change that to a 3. And then hit next. And so now it's going to have the cubed and all that kind of stuff. So A3 is the thing in front of the cube, which is a 4. A2 is what's in front of x squared, which is 0.4. A1 is what's in front of x. We don't have an x. So I'm going to put a 0. And the other one is the constant. So negative 6.5 times 10 to the negative 6. And we're going to hit solve. Oh, I had an accident. Oh, I didn't put the times 10 to the end. Negative 6. Then hit solve. Okay, so we're going to get 3 answers, and you have to know that the ones that have negatives in there are not going to make any sense. So the only one that makes any sense is the 0.00395. Alright, so that was a lot of math work to go to. But we're going to go back to this assumption that happened before. The KSP is pretty small, which means the x that spits out is pretty small. You can never assume away something that's multiplied, because the magnitude of that matters a whole lot. But when you're adding it to something, if you're adding 0.1 plus this number, that's pretty much going to stay 0.1. It's going to be 0.10395. So what we're going to go back and do is this part right here, we're going to say 0.1 plus x is approximately going to equal 0.1. And we're going to simplify this entire expression before we would have done it. I just wanted to show you that it was okay. And you would assume this away before you did this whole mess of math. Okay, and so now I can multiply that out with 4x squared, and 6.5 times 10 to the negative 6 equals 0.4x squared. And now all we have to do is take, I'm going to have to quit out of here, and do 6.5 times 10 to the negative 6 divided by the 0.4, and then we're going to have to square root it. And our x is 0.00403. And if you look at where we got once we did all that cubic stuff and the giant mess, those are pretty darn close. And we got a lot easier math, okay, with none of the polynomial root finder stuff, and that's our x. So it asks for the solubility of calcium hydroxide. So we found x, okay, which is going to be our solubility. That's how much is going to spit out. Okay, that's how much will have dissolved, because this was there in the beginning, but this is really the change. That's how much actually dissolved. Okay, so that's our solubility, and it's in molarity. And we already did the calcium hydroxide problem. Okay, so if we go back and find what we did with calcium hydroxide ahead of time, right here, the solubility was 0.0018. That's correct. Hopefully I did my math right. Okay, I had to go back and correct that concentration. I had written down the answer incorrectly the first time, because something wasn't right. I had missed a 0, or added a 0. So if we look at the concentration that was originally, if we just put it in pure water, we got 0.018 molar to dissolve. But when we put it in a solution that already has calcium in it, we only get 0.004 molar to dissolve. So it's a little less than half of what would have done before. Okay. So we're going to try one more and compare it to water and the common ion. So to improve the quality of X-ray photos used in the diagnosis of intestinal disorder, the patient drinks an aqueous suspension of barium sulfate. The barium ion in the suspension is opaque to X-rays, but it is also toxic. So the barium ion is lowered by the addition of dilute sodium sulfate. What is the solubility? Here's the question. Solubility of BaSO4, and they give us the Kp, in pure water, and then in 0.1 molar Na2SO4. So we're going to write a solubility equation, BaSO4. Okay, and our Ksp is 1.1 times 10 to the negative 10th. And our Ksp equation is going to be Ba2 plus times SO4 2 negative. Alright, so in this first one, if you put it in pure water, we don't care about the solid, there is no barium and no sulfate. We go plus X, X and X. And we simply plug into our Ksp, 1.1 times 10 to the negative 10th equals X times X. So all we have to do to find X is square root 1.1 times 10 to the negative 10th. And we get 1.05 times 10 to the negative 5th. And that's molarity. And so it wants to know the solubility of it, and either one of these X's is in 1-to-1 ratio with it. So there's your solubility. That much will dissolve in pure water. So the only difference about a common ion is when you set up your ice diagram, okay, we still don't care about the solid. There is now, this is the common ion. They both have sulfate in them. We don't care about the sodium, that's always soluble. We don't have any barium in there, but originally we had 0.1 molar sulfate. So when we go through this, we go plus X, X, plus X, and we have 0.1 plus X. So if you looked at what happened before, X was pretty tiny. If you compare X to this 0.1, 0.1 plus X is going to be about 0.1. So when we set up our Ksp, when we plug in there, we're going to go 1.1 times 10 to the negative 10 is equal to barium, which is X, and we're going to say this one is 0.1, but the X is not going to change the sulfate by much. And now when we solve this, all we have to do is dissolve or divide 1.1 times 10 to the negative 10th by 0.1, and we get 1.1 times 10 to the negative 9th molar, which is the 1-to-1 ratio of this, which is 1-to-1 ratio of barium sulfate. That's how much will dissolve. That's 10,000 times less than would have dissolved in the first place. Okay, so having that already in there lowers what you can dissolve. That's what the common ion effect is. So if you already have an ion in common with what's trying to dissolve, it will shove the reaction back to where it was. It won't let any more happen. So that is Ksp for the beginning. Hopefully that's all you miss.